Assalamualaikum warahmatullahi wabarakatuh. I am Nur Suhada binti Azmi. Today I will be presenting my final year project, which is a review on the comparison between the efficacy of Glyphilium trebium and Phaneroshid chrysosporium in remediating DDT contaminated soil. DDT is extensively used worldwide in the last century due to its effectiveness as insecticides and its ability to combat mosquito-borne malaria. It is an ideal pesticide due to its A. Low cost and ease of production, persistence, effectiveness against a wide range of insects, and low toxicity on human during that time. However, due to the mounting evidence of the toxicological and environmental effects of DDT, its usage has been banned in the 1997. However, the exposure towards this pesticide remains through its metabolites as they have been detected in the sediments and river water all around the globe. Mycoremediation is a type of bioremediation in which fungi or its derivatives are employed in the remediation of environmental pollutants. Mycoremediation is cost-effective, eco-friendly, and effective in removing such pollutants. The remediation of environmental pollution through mycoremediation is possible due to the production of enzymes by the fungi itself, such as lipase, lacase, and manganese peroxidase. The toxic compound recalcitrants can also be overcome by fungi through its variety of mechanisms such as bioadsorption, biomineralization, and biotransformation. Now we will look at the problem statement of this study. First, the accumulation of DDT in the environment has become an environmental concern due to the increase of health hazards connected to the soil-borne DDT exposure. Secondly, the existing physical and chemical techniques or methods that has been used to treat DDT contamination are generally destructive and intrusive to the target soils. We have seen the problem statement. Now let's take a look at the significance of study. First is better approach for the remediation of DDT in the soil. This is because mycoremediation is less energy intensive and time saving. Because if we compare fungi to other bioremediators such as bacteria, bacteria needs to be pre-introduced to the pollutants that are to be degraded before the actual remediation process. This would definitely delay the remediation process and requires more labor. Second is the ability of the fungi to remediate recalcitrant pollutant. White rot fungi are efficient in the degradation of a wide range of organic molecules due to the production of enzymes such as lacase and due to its simultaneous oxidative and reductive mechanism. Brown rot fungi, on the other hand, are able to degrade pollutant compounds through the usage of hydroxyl radicals produced by Fenton reaction. Moving on, if we take a look at the following table, in Malaysia, pesticides such as DDT were detected in the water sample taken from Selangor River. And high DDT value were also recorded at Kuala Terla Station in Cameron Highland because of the past usage of DDT in the agricultural area. In addition, in 14 provinces of China, concentrations of DDT exceeded the risk screening value. Next, I would like to move on to the effects of DDT exposure towards different target organisms. Firstly, DDT exposure have carcinogenic risks on humans. Secondly, for the wildlife, DDT exposure can lead to thyroid disorders, interfollicular fibrosis, and pregnancy impairments, especially in cows. As for the environment, DDT exposure can lead to soil infertility if there is high residue of DDT in the soil, and this would definitely result in food insecurity, especially to those countries that are highly dependent on the agricultural sectors. Finally, we will look at the comparison between the percentage of DDT degradation using Glyphilium trebium and Phaneroshid chrysosporium. For G trebium, with the addition of Fe2+, 64% of DDT is degraded, with DDE, DDD, and DPP as metabolic products. Meanwhile, without the addition of Fe2+, 58% of DDT was degraded, with DDE and DDT as metabolic products. So the addition of Fe2+ here means Fenton reaction, in which FeSO4 was added for iron-dependent process. In the absence of FeSO4, DBP was not found as metabolic products, indicating that DBP is formed by an iron-dependent process. No significant variations in the results were recorded, as we can see in the table, when Fe2+ was added, showing that G-terbium can be utilized directly for the degradation of DDT in soil without any additional treatment. On the other hand, for the degradation using p-crysosporium, through co-remediation with lacase, 66.46 DDT is degraded, with DDE and DBP as metabolic products, and without lacase, 45.35% of DDT was degraded, also with DDE and DBP as metabolic products. So the reduction of DDT concentration using p-crysosporium and lacase is greater than when using only the fungi or only using the enzyme. Therefore, co-remediation using p-crysosporium and lacase together can decompose DDT in soil faster and more efficiently. As conclusion, I would like to point out that both G-terbium and p-crysosporium has great potential in the remediation of DDT-contaminated soil. However, the remediation using G-terbium would be faster and more efficient, as no additional treatment needed when compared to p-crysosporium. The extensive research and application of this fungi would definitely be a breakthrough in the efforts of scientists to remove toxic pollutants from the environment. Before we look at the video clip that I've attached for this presentation, I would like to first point out the gaps and recommendations for this topic. So this method, remediation using G-terbium and p-crysosporium, has only been applied for the remediation of DDT contamination in soil. So it would be necessary for more research to be done or conducted into the utilization of this method for other type of medium, such as water, to see the potential of this method to be applied in the treatment of DDT in contaminated water, for example. Next, more research should be done for the utilization of other species of brown rot fungi and white rot fungi in remediating DDT contaminated soil.
Was the following. The farmer would spray DDT on his crops, and in fact the DDT killed the insects, but trace elements of the DDT would get into the ground, and the rainwater would carry it away, and those trace elements of the DDT would end up in the lakes and the streams. The fish in those lakes and streams would swallow the water, including those very minuscule amounts of DDT. The eagle loves to eat salmon. Oftentimes it would eat salmon that was infected with minuscule amounts of this DDT, and that created the problem. You see, when the eagle would eat this fish, that DDT would get into its body, and when it would lay its egg, the egg shell was just slightly too thin. Hence, when the eagle would sit on the egg to incubate it, to keep it warm, it would crack the egg, and the next generation wouldn't come about. Once the DDT was stopped, eagles no longer ingested it. They no longer had the weakening, the thinner shell. They produced fully robust eggshells, and the next generations were born. The eagle population responded and rebounded beautifully. Now, here's the very interesting point. The eggshell is the geometrically perfect shape to keep the baby inside, keep the weight of the eagle supported, and yet gently spread out that weight. It's just the ideal shape that will allow a heavy mother to sit on the egg without crushing it. But the eggshell has to be the right thickness. With the DDT in the body of the eagle, the eggshell was just a tad too thin, and even though it was an ideal shape, nevertheless the mother eagle crushed the eggshell. Once the DDT was removed, the body of the eagle began producing the correct thickness of the eggshell, and now, in fact, the eagle has rebounded.